Hello, welcome back to the session number 4 with the title Validating R&D with the Industry. I present myself, I'm Michele Tedesco, Metals Department Manager inside the CRF, that is a Stellantis company, and from this year, the Global Manager for the Metals topic. Today we will see this different presentation. The first one is presented by Begoña Casas. She is working on Eurecat Research Center, following the FormPlanet project as technician, as the technical coordinator of the project. The title of her presentation is Key Success Cases Across the Whole Sheet Metal Forming Value Chain. So I leave the floor to Begoña.
Thank you very much, Michele. I'm going to present the demonstrators of the FormPlanet. As we have mentioned it during this day, we performed some demonstrators, in specifically 19 demonstrators from different sectors and metallic alloys, to prove the effectiveness of the developed advanced testing methodologies and the modeling approaches. These demonstrators covers the whole value chain of the sheet metal forming industry, including sheet material developers, part makers, and also end users. Concerning sheet material developers, we have applied different characterization methodologies and simulations to try to optimize the forming processes of high-strength sheet metals, has, for example, advanced high-strength steels, different aluminum alloys, multi-layered sheet metals, and also cold-rolled steels, stainless steels. 2 case studies were performed with the company Aludium. Is an industrial partner of the project and produce aluminum alloys. And this case studies concerned automotive and cosmetic packaging sectors. The first one, in this first one, we have predicted the edge cracking resistance of a new aluminum alloy by the evaluation of the fracture toughness using the methodology based on the essential walk of fracture that was explained before in the session 1. The second case study related to cosmetic packaging. In this case studied, we performed miniaturized tensile tests that were also explained by Contes before, for the quality assessment of aluminum 5657 used in a cosmetic packaging product to try to reduce the appearance of cracks during forming operations. Also, another sheet material developers is ArcelorMittal. It produces steels for automotive applications, and the case studied in this consisted of the prediction of crash performance in advanced high-strength steels for hot and cold forming through lab scale testing methodologies. Another case study was done with Lamera. They produce multi-layer sheet metals for automotive applications, and it is in this case studied, we predicted the formability and performance of a multi-layer material developed by them through finite element simulation and evaluating also the mechanical properties through advanced characterization tests based on end user requirements. With Arania that produce cold rolled steels for automotive applications, we studied the effect of the skin pass reduction. There is a final step on the manufacturing route of cold rolled steels by the performance of drawability test and accurate mechanical characterization. Also with Arania, we performed another case study related with the prediction of the behavior of of the prediction of the behavior of material for fine blanking operations through the performance of the fracture toughness evaluation test by the essential work of fractured methodology. With Replacer was one of the selected companies for the open call that they produce hybrid composites. This case study, the sector was for the home appliances, and we evaluated the formability of a novel sheet metal product that consisted of two metallic coated layers bonded by an adhesive by the performing of the drawing test and the bending test. With part makers, we have performed, or the test site have performed tests and simulations to try to improve the manufacturing processes of complex parts with high-strength sheet metals. One of these case studies were done with the company Arcelic. They produce home appliances. We work in the characterization and optimization of the clinching process in the manufacturing of washing machine drums with advanced mechanical characterization tests and also with FEM. Another case study were done with CRF for automotive applications. In this case study, we verified the potential of the FormPlanet methodologies to predict the edge cracking phenomena in a T-node geometry part that represents the upper part of a card B pillar component. Another part makers case study was done with AP&T for automotive applications. In this case study, we assayed the reduction of the tried out time of hot stamping dies by applying a FEM sheet forming simulation model based on material characterization data and forming parameters obtained during the hot forming process. Another case study was done with STAM. This is another company from the FormPlanet, another planet of the FormPlanet, also for automotive applications. And in this case study, we performed the analysis of the cause of cracking issues during forming operations of automotive thermal and acoustic insulation parts through the mechanical characterization test and modeling developed in the project. Another company that was selected during the open call is called Aerobase. The sector is transport, and for this case study, we performed the characterization, material data characterization of aluminum alloy 7075 for the development of a physically based model for isotropic hardening, anisotropic yielding, and failure of an aluminum plate material used in structural components. Another company selected in the open call was Casconos Holding, also for the transport sector, and for this case study, we characterize press hardening steel by fatigue. We measured the fatigue resistance, the hydrogen susceptibility, and also performed process modeling of a novel developed martensitic high-strength steel. Another company selected in the open call was Stamp for automotive applications, and with them we study the combined influence of the pre-strain and the trimming of the edge ductility of high-strength steels. Other company of the open call was MA for transport applications. We characterize press hardening steels. To do that, we performed finite element simulation forming, edge flangeability tests, diffusible hydrogen measurements, with the idea to prevent cracks in the flange area of a component manufactured by the press hardening steel process. Other two part makers that were awarded in the open call were Mubea for transport applications and Paul Welding for machinery and manufacturing applications. With Mubea, we have optimized the forming process of a laser welded steel tubes with flattened ends made by cold stamping. In this case, we performed miniaturized tensile tests, finite element analysis, and fatigue tests to characterize and optimize this process. In the case of pole welding, we performed an optimization of lasered welding. We evaluated the mechanical properties of the joints formed by lasered welding with metal sheets made of stainless steel, structural steel, and aluminum alloys to optimize the laser welding parameters. And finally, concerning end users, we performed two case studies. In the case, one of them with CRF for automotive applications, and this case study consisted in the implementation in a real production plan of an equipment for the monitoring of hydrogen content in raw materials and stamped components for transport body in white parts made of UC board 2000. And the last case study was performed with Arcelic in the sector of home appliances. And the idea here was to improve the forming behavior of a refrigerator compressor shell. We investigate the cause of tearing and thickness reduction on the surface of a refrigerator compressor shell during the deep drawing via sheet metal characterization test. These are the 19 demonstrators that we have performed during the FormPlanet in both in the task of the FormPlanet, but also in the task concerning the open call, and that's helped to validate the characterization methodologies and modeling approaches that we have developed in FormPlanet project. In this session, in last sections, some of these case studies has been explained a little, and also in this session, some of that will be explained with some more detail. But you can find all the information in the case study catalog available at the info point. Thank you very much for your attention.
Thank you, Bego, for your interesting presentation and to have give us the opportunity to discover all the test case analyzed during the FormPlanet projects. Okay, so now is my time. In this presentation, as anticipated by Begoña, we will see the hydrogen monitoring in press-hardened steel used for body-in-white components. This is the agenda. We will see briefly what we have done on using the UC 2000, that is a new press-hardening material. The measurements that we did together with Latomec about the diffusible hydrogen on the stamped component and the raw material, and finally the conclusion. First of all, the goal of this study is to implement in real production plant a control of hydrogen, diffusible hydrogen, to prevent the delay cracking due to this kind of elements. To do that, together with FCA, ex-FCA, now Stellantis manufacturing department, we select the best material that could fit this kind of experimentation. At the end was chosen the A-pillar reinforcement of Fiat Panda. For this purpose, 100 blanks were stamped using UC 2000 in ex-FCA plants, and on that, together with Latomec, we check the value of diffusible hydrogen into the raw material and on the final components. Here some pictures as the material arrived in our plant. Thanks to the collaboration with ArcelorMittal, they provide us the blanks directly laser cutted to be stamped as it is, and each blanks was marked with several codes that specified different conditions of the process. The condition that and the parameters that we studied during this activity are different. We focalize our attention on the two different parameters. The first one is the dew point control that we have in the oven, and the dwell time, so the time that the blanks stay into the oven. The dwell time usually for the pre-hardening component with a thick layer of coating is between 300 and 600 seconds. While the dew point generally is set up around -7, -5 grades centigrade. But we tried also to modify this parameter to see what could be the results on the final component. Based on that, we would like also test the worst condition that is indicated as number 5, in which we turn off the dew point control in the process. We leave the blank at the maximum time in the oven, and as plus, we sprayed water on the upper side of the blank. This to test the limit of this material and of our process. Before stamp the component, we did together with Latomec the measure of diffusible hydrogen on the raw material as we received in our facilities. To do that, we used the Helios 4 system without removing the surface coating, and we found that the material was very clean, very poor diffusible hydrogen was detected, less than 0.1 part per million. After the stamping, we performed the same analysis, so the diffusible hydrogen measurement on the stamped component in different areas of for each component. Because changing the areas, also the concentration could change, because the cooling under the die is not uniform and depend on the shape of the component that we are stamping. Here are listed the results for all the components tested in the different conditions, and with the red circles, we can see the worst result, where we found a high value of hydrogen compared to the other one. So the first samples is the number 2, in which we set as parameter the dew point off, and we leave the blank at the maximum time into the oven. And the second component where we found a high value of diffusible hydrogen was the samples number 5, the component that was stamped without the dew point control, leaving the samples at the maximum of the time, and also applying the water spray. After this characterization, looked at what was the maximum value of diffusible hydrogen absorbed by the material, we carry out together with Latomec and the University of Pisa the slow strain rate test to see if this quantity of diffusible hydrogen could have an effect on the mechanical properties of the material. The results was very positive because the mechanical properties still remain the same of the virgin material, and so this means that the material also in the worst case is in the safe condition. For this reason, the material engineering of Stellantis give the validation of Usibor 2000 to Arcelor. In conclusion, we can say that there is a non-destructive method to control the hydrogen content into the material before and after the hot press forming. Knowing the hydrogen material threshold is possible to prevent delayed cracking of the component by checking the component after the hot press forming. So this gives us the opportunity to have claims after the component production. The Usibor 2000 shown an excellent behavior, also in worst condition, so it was approved by Materials Engineering of CRF and Stellantis, Stellantis company. So we will plan to use soon this material to reduce the weight of our future car. Okay. So the next presentation is led by Ramin Moshfegh. Ramin is graduated in mechanical engineering in 1994, obtained his PhD in solid mechanics at the university in Linköping. For the past 27 years, he has held various positions at the university, research institutes, manufacturing industries, and associated R&D center. Since 2016, he has worked as CTO at Lamera. The title of his presentation is Pre- and Post-Experimental Investigation and CAE Tool for the Formable Sandwich Material Hybrix. I leave the speech to you, Ramin.
Okay. Thank you very much, Michele. Thank you very much for the introduction. And I want to mention the co-contributor for this presentation too. The first one is coming from Lulu University, Department of Solid Mechanics, and after that the CRF. You help us with this project, and the last one is Eurecat, who work in this project in different way in order to make a material characterization, especially in failure. This is actually the outline of my presentation, very short about the company I am working for and about our product, challenges as engineering solution for lightweight material, experimental investigation, and material characterization by third party as we are a member in this project. And we try to exemplify and show capability of the material by using the battery box cover as a demonstrator. And we want to third party make evaluation of the result and performance of the product, which is CRF done for us, and some summary and conclusion of the work we done together. The company is Lamera, which we develop and manufacture and market lightweight material under brand name Hybrix. And the production site is here in Gothenburg. The Hybrix material, the total concept of the material is actually this a patented micro sandwich technology. If you compare this material with a solid sheet metal, so you can actually save the weight between 35 to 75% by using Hybrix, and it's highly dependent on which type of component you want and the application area. And the manufacturing line, as I mentioned, is a huge capacity and deliver high quality of the material. This is about the company. And which challenges we have actually. We know that the industry is focusing on lightweight product, and they try to find a different solution actually. For example, using the multi-layer material, so the metal matrix composite, a pure sandwich material, or metal foam or material with tailored properties, in order to see how they can find a proper solution for lightweight. They're using different types of manufacturing processes, for example, hot forming, so we heard today, and using different type of the assembly technology, for example, so multifunctional adhesive or part integration, and so on. The chart to the right shows very simply how much we gain in percent if we reduce the weight of the material in automotive, and for each percent we can reduce almost 10% of the mass weight, 10% of the fuel consumption actually. So if we have a 2 tons vehicle and we reduce almost 8% of the vehicle weight, so we're talking about 200 kilograms. So we have 400 kilograms. So we can see we can reduce that almost with 10 to 20%. So that's very important for the automotive industry to find some good solution in order to reduce the weight of the product. And all those, you can see that there is a many challenging part when you want to introduce a material especially for automotive industry and those other products. For example, is it good enough to implement this material? Is the under generation of the product, is it fit our traditional production line? How we can make assembling, time construction and design, cost, and many other things. And one of the tools we are using actually is the CAE and computational based design, which is a very central knowledge in automotive industry especially. And what is our task here in order to eliminate all those obstacles we have is actually develop an experimental method to capture the mechanical properties of the material, especially shear condition for sandwich material. And it was a very cost efficient way to make such an experiment. The most of the experimental setup I could find in the literature, university, as everywhere. So it was so cost efficient. It takes so long time in order to get only the result. So that's not good at all for SME. And in the same manner, we should look at how we can use the CAE tools in order to catch or predict the result from multi-layer material with high or large deformation and with high accuracy, for example, double procedure result, and we can use a different constitutive model and predict corrosive failure and instability. So I call that this is a process route with a 10 step. Only that one is the experimental investigation, which we done in cooperation with Eurecat and Lulu University, and especially Lulu University was the main part of this part. And here we can see that 10 step. So you can allocate the result or experimental result for the material and use those results directly in your simulation tools. Here at the end, you can see the material card, how we use for our simulation model. Of course, when we're talking about a new material, so they should fulfill many requirements. For example, for example, is it able to catch the side impact analysis? Is it good enough with dead weight? And what happens if you have a target or impact coming under the battery box, and what happened if somebody dropped that one to the floor? So all those things, we made our simulation job in this project, and we can see how we can design the stamping tool for that one. For this purpose, so we made the different type of the sandwich material. We call that CC 0.2, 0.2 PC 120, and simply that's telling us that this is a carbon steel in both sides. The face material thickness is 0.2 millimeter. The core is the fiber core, especially for Hybrix. We have the different type of the adhesive system. This is a C adhesive, and 120 talking about this is the total thickness is 1.2 millimeter. So, and we made all those battery boxes based on those configuration, and sent those numbers of the material directly to CRF in order to see if it's good enough or not. This is a tooling setup we have in order to make the physical trial and make a specimen at our company. And here we can see the form part which we delivered directly to CRF. And one of those important validation aspect was that make a SMT, standard test method, in order to see that product is feasible after the forming process, before forming process, and what happened with the material, is it durable or not, actually. And simply CRF take care of that one. So you can see that they made the non-destructive control, micrographic analysis, and the STM D1876. And it was very interesting for us that they made the experimental procedure in different temperature configuration, which is somehow pretend that we are in the working with the forming process, and we are going from the painting process. So you can see that at a room temperature at 45 degree and bake hardening, simulated bake hardening. And you can see that the load per weight values is clearly fulfill the requirement CRF has for, in order to say the material is okay, coming to our material department, and we can start to work with that one. We made an experimental procedure for thickness reduction, and we could see if they take the material directly from different part of the form product and make a measurement if material lose the performance basically after the forming or not. And that showed that's good enough, actually. So finally, in conclusion, I can tell you, I don't need to go through all those things for you. That is, we could make a lightweight product. We establish a methodology using the CAE tools in order to make the feasibility analysis of the product. Two different software used, Elastina and Impetus, because we want to know that this is not only one software show for end user. We establish a new experimental setup. It actually is very cost efficient, and we know how we can do that. It's very simple to produce that tooling setup, and we made the robustness analysis in order to see the repeatability of the product. And we also was happy to our third part project member could make experimental evaluation and validation of the product. Thank you very much.
Thank you very much, Ramin. So now is the turn of Vedran Kovacevic. Vedran, master degree in mechanical engineering and the Lund University. He is part of R&D team of AP&T department, forming technology as a research and test engineer. He did the main research about aluminum and composites material. The title of his presentation is FEM modeling for hot forming application of high-strength aluminum sheet by implementing real process data.
Thank you, Michele. And within the FormPlanet project, we investigated how to reduce the tryout time for tooling applications, as this is a costly procedure in the sheet forming industry. The goal was to implement a simulation step into the conventional tryout process in order to reduce the tryout time by 50%. The solution to this was to build a FEM sheet metal model into which parameters from practical forming trials along with new material cards were implemented. FEM models were built for two hot-formed high-strength aluminum grades, namely AA7075 and AA6010. The practical forming trials were executed in AP&T's aluminum test line. The test line is equipped with a multi-layer convection furnace and a 600-ton servo-hydraulic press. To execute the trials, we used a scaled car door ring to form parts with a sheet thickness of 2 millimeters. The following test procedure was implemented. First, the blanks were heated in the MLF to a solutionizing temperature of 560 degrees for AA6010 and 480 degrees for AA7075. The blank was then transferred from the MLF to the tool in the press, where it was formed at an average speed of 100 millimeters per second, followed by quenching at 600 tons for 10 seconds. We formed 3 parts from each alloy, respectively. Throughout the practical trials, we measured various parameters, but 2 of the most influential ones are the slide speed and the cushion force from the press. Both parameters are constant set values to control the press, but the actual output yields a non-linear result. After forming, the tool's surfaces were 3D scanned in order to visualize the difference between the nominal CAD geometry to the actual tool geometry. The scanned tool surfaces were then meshed and imported into the simulation software PAMSTAMP. Apart from the tool scans and the press kinematic parameters that we gained from the forming trials, the FEM model would be incomplete without the proper material cards for the alloys. From previous work, AP&T already had access to heat transfer coefficient depending on gap and pressure for the alloys, but lacked flow curves and anisotropy values. Therefore, together with our project partners Fraunhofer and Comtess, we defined a characterization matrix for hot tensile tests that were performed. Fraunhofer performed tests for AA6010 and AA7075. They were performed at different temperatures and strain rates according to the tables in order to obtain the data needed to describe the plastic behavior in the material at elevated temperatures. By implementing the true stress strain curves gained from the experimental results into the Hockett-Sherby equation, it was possible to extrapolate flow curves to higher strain values for the alloys. In addition to the hot tensile tests, Fraunhofer also performed hot tensile tests in 3 different load states to describe the forming limit characteristics of the alloys. This was done for uniaxial strain, plane strain, and biaxial strain. Unfortunately, due to equipment restrictions, the strain rate used during these laboratory tests for the 7000 alloy was very low. And as will be shown in the result later, this does not reflect the real strain in the material behavior for this hot stamping application. Comtess had a different experimental approach for the hot tensile tests. They performed the tests on the 6000 alloy. The main difference being that the hot tensile tests were conducted at different strain rates and at a wider temperature range than from the tests from Fraunhofer. In addition, they used a different method of heating up and cooling down the samples during the experiment. After we formed all the parts, we also scanned the formed parts in order to have the sheet thickness information of them. The scans were used to validate the FEM simulation by comparing the sheet thickness of the formed and simulated part. The regions marked in red show a tendency of high thinning, and together with the regions that exhibit a crack for the 7000 and strong necking for the 6000, they can be used for validation. Coming to the results for 7000, or I can mention that we used the material model Barla 2000 for all simulations, and looking at the result for the 7000, comparing it with the 3D scanned formed part, it shows a quite accurate outcome. There's a deviation of plus minus 0.2 millimeter, which is acceptable. In the region where the crack occurs, in the simulation, there is a strain rate of 0.001 per millisecond. Since the time unit system in PAM-STAMP is milliseconds, this equals to a strain rate of 1 per second. And applying the FLC data from Fraunhofer to the result shows that this zone is safe, which is not the case as the crack occurred here. And the reason for this is, as mentioned, because of the low strain rates used during their experimental tests at Fraunhofer, which is lower than the strain rate during the actual forming procedure. Looking at the 6000 result, the simulation also show accurate thickness behavior. The deviation in the critical zones is within plus minus 0.2 millimeter, and the zone where the strong necking occurs is validated with the FLZ data from Fraunhofer. Moving on to the tests using the material data from Comtess, we can see that they display a different result. It may seem that this card has an improved performance as the deviation from the nominal 2 millimeter thickness is better than for the result using the material data from Fraunhofer. But this is in fact misleading because there is considerable thinning in reality in the region that were marked red in the previous picture, especially where the strong necking occurs in the simulation using the Comtess card. There is only a thinning of 20%, which is incorrect. Moreover, applying the FLC data from Fraunhofer to the simulation shows that this region is marked as safe, further indicating that the material card has reservations in terms of accuracy. To sum up, the simulation results for both aluminum alloys show promise in terms of thickness behavior compared to the formed parts. However, it is challenging to apply the same process route, which is usually present in an industrialized hot forming process, to the hot tensile tests conducted by Fraunhofer and Comtess. Further, it must be highlighted that the flow curves describing AA6010 were determined using different experimental approach, strain rates and temperatures between Fraunhofer and Comtesse. Therefore, the results may not be fully equivalent for both simulations. The materials were described as isotropic in the simulation, which also might lead to less accuracy of the calculated results. In future project, an anisotropic characterization of the material should be investigated, of course. The friction coefficient is one of the most impactful parameters in hot forming. In the simulation, it was assumed to be constant. However, in reality, the friction depends on temperature, speed, pressure, and lubrication amount. The friction affects the drawing of material and in the end, the thinning and thickening results. To conclude, the simulation results are satisfactory in terms of feasibility analysis to predict the thinning and thickening behavior of the part. The material input data from Fraunhofer and Comtesse can be used for future work and forming simulation of other part geometries. After the submittal of the report, we also made a virtual tool compensation in order to see if there would be a better contact distribution between blank and tool surfaces. And as seen in the image, it is quite clear that the contact after the virtual tool surface compensation is better, as the temperature distribution on the tool surface is more even. The next step would now be to investigate the impact on springback after the virtual tool compensated surfaces in the simulation. That was all from me. Thank you, and I welcome any questions you might have.
Okay, thank you, Vedran. The question will be at the end of this section, so can be addressed there. Now is the turn of Catalina Fernandez Rivera. Catalina is Aludium Research and Development Director. She has a PhD in Master Science, and she has been working for more than 30 years in the aluminum industry, involved in process improvement regarding smelting, casting and rolling, and managing the new product development for different aluminum segment markets. So the title of her presentation is Edge Cracking Prediction in the Aluminum 5754, alloy for automotive components.
Thank you, Michele. Well, as commented previously, Aludium is one of the industrial partners in FormPlanet. I will present you one of our case study, where the target was to predict edge cracking, a common issue in metal forming. First, a short presentation regarding Aludium. Aludium is a leading provider of aluminum-rolled products for different markets, such as automotive, industrial, building and construction, decorative, or cosmetic packaging. Here you can see our case study. The problem is edge cracking in a stamped piece in 5754 alloy H111 temper, the most common not heat treatable aluminum alloy and temper used in automotive to produce medium strength pieces. During this case study, a new version of the 5754 with a special chemical composition and thermomechanical route was tested and compared with the standard material. Fracture toughness, the most suitable fracture parameter to predict edge cracking in higher strength metal sheets, was evaluated using a FormPlanet in-house methodology based on the essential work of fracture. In Aludium, facilities were determined the chemical composition, microstructure, and standard mechanical properties of both materials, called OK and no OK in this presentation. In the trial material regarding chemical composition, the main hardening element, the magnesium in this alloy, was kept at the same level, but the amount of iron and silicon main impurities was reduced. Both materials present a fine recrystallized grain structure, ASTM number 8 and 8.5, quite similar. But as a consequence of its higher purity, the new material shows a slightly coarser grain size, detrimental for stamping process. Regarding the tensile test, the results are quite similar. Also, we can conclude in this first part that the standard metallurgical studies are not able to predict the edge cracking. Now I will pass to present the result of the essential work of fracture that allows to evaluate the fracture toughness. Here you can see the dent specimen and the experimental determination of the essential work of fracture. Samples with different ligament lengths are tested at a constant displacement rate, obtaining curves as is shown in the middle that represent the work of fracture for the different ligament lengths. Then integrating the area under the load and dividing by the initial ligament area, the specific total work of fracture is obtained. Finally, plotting these values against the ligament length, the intercept marks the specific essential work of fracture, while the slope is the plastic work, as you can see on the right. Well, now the result of aluminum material. Here you can see the load versus the displacement curve for the OK left and no OK material. The area under each curve, the work of fracture, is much higher for OK than for no OK material. And when the specific total work of fracture is plotted against the ligament length, we can see a clear difference in values obtained for fracture toughness, 148 versus 71, in plastic work, 21 versus 14, as well as for the fracture toughness at crack initiation, 106 versus 64. Here is a graph summary of the result. The conclusion that we can take from this test, the essential work of fracture, is that the OK material shows a higher fracture toughness and plastic work than the no OK material, and also that more energy is needed to propagate the crack after initiation in the OK material. And finally, our conclusion regarding the FormPlanet test used in this case study is that the essential work of fracture test provide a simple, a faster experimental way to understand the cracking behavior of material during metal production or forming, while microstructure studies and standard tensile tests are not able to explicate this data. Also, these tests permit a more cost-effective and rational development of new thermomechanical processes and products in aluminum alloys. Thank you.
Thank you very much, Catalina. And now, last but not least, Jean Lamontanara from MA company. Jean is degreed in mechanical engineering in 1987. He has a PhD in mechanical materials engineering in 1994. Start working in Ugine Research and Development Technical Center as responsible for the electron microscopy and image analysis. In 2000, became the resident engineer of ArcelorMittal for Fiat in Turin, and in 2012 he became responsible for product engineering and innovation for MA company. The title of his presentation is Hydrogen-Induced Delayed Fracture on Press Hardening Steel.
Thank you, Michele, for your kind introduction. So here you can see my agenda. So first of all, I will say a few words about the company, the products of my company, and going deeper in the hot forming process. After that, some explanation about the part we decided to put as a case study together with FormPlanet Consortium. The measurements and the results in terms of diffusive hydrogen, and at the end, some discussion and conclusion. So about the company, so MA CLN Group is a company that we have 3 divisions. We have metal forming, meaning stamping for automotive, name MA. Company MW producing steel wheels, and after that we have some other division dealing with steel distribution. Also, we have a central lab here in Torino. Here you can see our footprint. So we have plants quite all over the world, following our main customers. So here you can see on the left our customers. So mainly Stellantis, Renault, and also BMW, Mercedes, and so on. And we are deeply involved also in commercial vehicles, light and medium commercial vehicles. On the next slide, you can see some view about the products of MA. So mainly the body in white for skin panel, structural parts, also for some chassis part. Going on hot forming, so for the hot forming, the facility is in Poland, in Tychy, so we are inside the Stellantis plant, and also working in close contact with the central lab we have here in Torino. Here some views about the line in Tychy. So on the top right, you have an overview of the line. So we have a long tunnel furnace with gas. We have hydraulic press and the exit. On the bottom right, some details about the machinery, about the hot blank out of the oven. Also, we have laser cutting. And you can see the parts we are producing right now. So some feature about the hot forming. So we have a hydraulic press, about 1,200 kilonewton power. We can process all kind of 22 manganese boron-5 coated, so aluminum silicon, meaning what are well known as UZ-bor 1500 megapascal, also UZ-bor 2000, and so on, for the range of material thickness from 0.8, 0.7 to 3 millimeters. The furnace is a furnace with 15 control zones, and we have a dew point control that we can guarantee less than -5 degrees. And I will go in detail about the dew point control. And right now, so we are producing more than 20 part number in serial life, mainly for Stellantis, so ex-FCA and ex-Peugeot. So here about the control. So in this facility, we have a lot of process parameter control, for sure, as Michele said, temperature, dwell time, and so on. But in the frame of hydrogen, a key factor is the control of dew point. So we have a built-in system in the oven. So we have a closed loop system. So the yellow image you can see on the middle is the dry air compressor. So we produce dry air that is put inside the oven in some area where we don't want to have hydrogen. And we have a system of measurement, and continuously we measure the hydrogen. So the dew point control is measured, and those data are recorded. Okay. Also, as I said before, we have many other process parameters under control, like temperature, speed, time, water, and so on. And all these parameters are recorded in special files. So about the case study, so we choose an interesting part with Letomec and Unipi. So here on the bottom left, you can see the part. So it's a pillar. The thickness is 1 millimeter. That is in serial life since 2-3 years right now. So we shipped some full parts to Letomec and also some samples that we laser cut in our facility. Okay, so we apply a special packaging and we deliver to Letomec. So some samples received the day after the production, so the day after the hot forming, and some other sample that arrived in Letomec a few days later, so around 5 to 6 days. Okay, so the samples arrive in Letomec for the measurement using the Helios hot probe equipment, as well described by Linda Bacchi. So here we have the results. So some areas were measured for the diffusive hydrogen, and we can see that on all the samples measured by Letomec, we have some very low values in terms of diffusive hydrogen. A lot of points are at 0 or 0.1, or maximum is 0.2. So we are quite happy. It's not a surprise for us, this kind of results. And here, this kind of results are put on this table. So we have the threshold here. The red line is the threshold established by Unipi, and the blue points and the red point, the measurements on our parts, and we are well below the threshold, well below. So we are quite happy again about this kind of results. So as a conclusion, we can say that the Letomec measurements confirm furthermore that our recipe, so the respect of, in particular, of a good dew point in the oven, that our parts are fully okay. And we can say that at this stage, we have no risk of delay fracture on the parts. So this instrument was very useful to confirm that the quality of our part in terms of risk of delay fracture, our parts are very good. Thank you for your attention.
Thank you very much, Jean. So now we can open to the Q&A section. I'm just seeing if there are some questions. Yes, a couple of questions to Catalina for his presentation about aluminum edge cracking. The first one that contains three questions. Why do you think impurities affect the fracture toughness? How are they distributed in the microstructure? Perhaps they can precipitate and facilitate the propagation of cracks.
Okay, the iron and silicon are mainly the iron is the most insoluble constituent element in the aluminum. So it is segregated since the first step of the solidification during the casting. So forming a constituent, quite a big intermetallic particle with together with the aluminum, the silicon, and sometimes with manganese. So these big particles create void during hot rolling and cold rolling. This is a preferential site to produce later on cracks during forming. So it's not a beneficial effect the iron in the semi-continuous casting process are not able to precipitate as a small particle precipitate, just constitute big particles.
Thank you very much, Catalina. And another question that contains 2-3 more questions for you. Fracture stress difference between not okay and okay alloys.
Mm-hmm.
The higher the fracture stress for the same tensile strength, the higher the edge crack sensitivity. ISO all expansion test conical expansion done between both alloys. Fracture areas reduction performed between both alloys.
Sorry, what is the question?
The question is if you did the all expansion test
Yes.
on both the alloys,
yes.
And if you perform the fraction area reduction on both the alloys.
Yes, in both tests were carried out at the first step of the FormPlanet project when we sent this type of material to the different test beds to test new method, the novel methodologies, and really the result extract from this type of tests were not so clear that the essential work of fracture. Thank
you very much, Catalina. There is another question to me. Had you used the Helios 4 in stainless steel? This is a good question, thank you. Today the answer is not yet. We focus our attention firstly for the component that we are using to limit the intrusion during the crash, so the press-hardening material. In the second step, we would like to analyze also cold forming steel used in the body in white to absorb energy during the crash or to limit the intrusion. And for sure, in the third step, we will consider also the stainless steel. So the answer to your question was not yet. No other question coming from the audience. I have just a couple. One to Jean. because we have seen during your presentation that the level of hydrogen is very low for the component that you analyzed. My question is how this testing method could be used in the automotive field, in your opinion, and what is the main benefit that you are looking using this kind of methodology?
Thank you, Michele, for this question. We can say that with this method, we have another method, a kind of direct method on the parts to check the level of hydrogen. For sure, as we saw here, if we respect, and also you showed this in your study, if you respect good recipe principles, mainly dew point, but also clean blanks and so on, quite for sure you have a good part. But if imagine there is something wrong on the oven that you don't know, maybe the system can say to you the dew point is good, but in reality the dew point is not good, or there is something locally bad in the oven. We have a device that you can check physically directly on the parts. So it is a more safe. It is safer to you have a higher level of safety to guarantee the good quality of the parts. And also you have a system that you can customize furthermore your recipe to be sure where we are respect to the threshold.
Thank you very much, Jean. Thank you. I have a curiosity also for Ramin and his Hybrix material, because generally in the automotive field, the main way to make the assembly is the resistance spot welding. So my question is if also the sandwich Hybrix material is weldable, or you are suggesting another way to assemble this kind of material?
Thank you very much for your question. This is a general issue. All those sandwich material has actually with common welding process. But the spot welding is not any problem. You can make a spot welding by integrating the material, which sometimes they call it the flex weld. So actually you bypass the upper side and lower side of the material together in order to make a spot welding. That's very common. And the other things is that if we have had this question for 10 years ago, it was dead answer. It's not good. But nowadays we know very well that automotive industry using a multi-material commonly, and they're using a different type of adhesive in order to find a solution for assembling the different part with the different type of the properties. And for example, composite material with aluminum, composite material with stainless steel, and so on. Stainless steel with aluminum and so on. So they have very good solution. And using the adhesive is very implemented strategy for automotive industry. So common way, the welding is not possible. Friction welding is not possible, but you have the different type of solution industry. Or commonly the mechanical joining. This is one of the most common way to work with the substrate. Thank you. I hope you'll get your answer.
Thank you very much, Ramin. It's a very clear answer, and you answered to my question. Thank you very much. And I have a curiosity also about the AP&T presentation to Vedran, because generally we work a lot on the hot press forming of the steel, less about the aluminum. And in general, when we are talking about the press hardening material, each of the suppliers or stampers say that the springback is not a big issue because it's near to zero for the press hardening of the steel. Looking at your presentation, I learned that is not the case of the aluminum. So I would like to ask you what is the main differences in the behavior of the steel and the aluminum under the die, and what's the strategy that the stampers can use to minimize this effect?
Thank you, Michele. Well, I'd like to think the main reason is that in hot forming of aluminum, usually the acceptable thinning can be quite high, higher than in PHS. And a higher thinning leads to worse contact distribution in the tool. And when the contact distribution is low, there will be a thermal distortion in the final part, which is causing the springback. So to mitigate the springback, the tool surfaces need to be optimized by die spotting, because they're rarely optimal after the first manufacture. And once they're optimized by the die spotting, the areas that contain the high thinning are compensated. This is why it is crucial to have accurate FEM models, for instance, that describe the thickness behavior well for hot formed aluminum in this case, as the thickness behavior serves as a base on how and where to compensate the tool surface. So by working proactively on having FEM models that can compensate the tool surfaces virtually, you can reduce a lot of time in trying out by practical rework of the tool in order to get rid of the springback in production. I hope that answers the question.
Yes, thank you very much.
Thank you.
So, no more question from the audience. I propose you a coffee break, and we will return at 4:30 for the roundtable discussion. Thank you.